Today, we are talking about ways to represent molecules and charge. But to think about charge, we need to first think about how much any atom wants electrons, or its electronegativity. Look at the electronegativity chart displayed. Which atom is the most electronegative atom? Which is the least electronegative atom? Write down these answers and bring them to class. Notice that in any group, larger atoms are less electronegative, and in any period, the atoms farthest to the right are the most electronegative. So in a column, the electronegativity goes down as you move from top to bottom, and in a row, it goes up as you move from left to right. We've already talked about how bonds are really pairs of electrons that are shared between two, or at least usually two, atoms. But because atoms have different needs for electrons, some atoms don't share electrons well. For example, the hydrogens shown here have electrons around them for exactly the same amount of time, while hydrogen and fluorine have electrons around the fluorine much more due to its larger electronegativity. We indicate this difference by a delta minus by the fluorine, indicating the negative charge, and a delta plus by the hydrogen. Using the electronegativity chart, indicate dipoles on the three bonds shown. Write these down and bring them to class too. Carbon is usually negative relative to hydrogen, but it quickly becomes positive when it's attached to Naufkälber, so things like nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Hydrogen is usually positive, but it becomes negative when it's attached to boron. Since opposites usually attract, we can tell a lot of reactivity with these general trends. With boron through fluorine, so this series right here, we can easily see what the relative electronegativity is from left to right. Boron is going to be the lowest of that series, and fluorine is going to be the highest. And with fluorine through iodine, we can also easily tell through the trends in electronegativity. Hydrogen is the only one that doesn't really fall neatly into that category, and so as long as we remember that hydrogen comes between boron and carbon, we don't really need an electronegativity table. We can tell what most of the polarity across most bonds are just by looking at the periodic table. Sometimes it's useful to represent charge along with a three-dimensional structure. We do this with an electrostatic potential map. On these maps, red means negative and blue means positive, and the in-between colors follow the rainbow. So yellow is more positive than green, but all those middle colors are relatively neutral. It makes for very pretty pictures. It also allows us to see which areas are most likely to react in a molecule. 99% of the reactions that we talk about in this class are essentially governed by opposites attract. Negative places on a molecule interact with positive places on a different molecule. Which of the displayed hydrogens of these on the slide would be most likely to interact with the CO2 carbon? Answer this and bring it to class. Depending on the extent of difference in electronegativity, we might actually consider the electrons to be fully removed from one atom and given to another. This is called an ionic bond. Notice that in this case, we write a full negative and a full positive charge on the ions. Bonds are not simply ionic or not ionic. There are grades of polarity from completely nonpolar to very strongly ionic. We arbitrarily define ionic compounds as those that have a difference in charge that is greater than 2.0. We don't really want to calculate this all the time. For the purpose of this class, we just assume that if a nonmetal and a metal are bound, it's probably ionic. One important exception is where instead of a metal, we have a polyatomic cation like ammonium, which would also be ionic. Generally, the buildup of charge is less stable than having a neutral atom. Formal charge is an important way of accounting for electrons in a given structure to see if that structure is stable. Formal charge is always a comparison between the expected value, how many electrons each atom brings to the molecule, and how many actually end up on an atom or ion. Notice that when we count electrons in a bond, we divide them equally between the atoms participating in that bond. Take this example for hydrogen fluoride. On a hydrogen, there are no non-bonding electrons. We'd expect one electron from H, and we get one from the bond. So the formal charge ends up being 0. Likewise, fluorine should have 7 electrons. We get 1 from the bond and 6 from the non-bonding electrons, and it has 7, and we end up with a formal charge of 0. Let's work through an example of drawing a molecule from a structure and then assigning formal charges on that Lewis structure. First, we're going to start out by drawing a Lewis structure. We have 3 nitrogens. We know that one of them has to be central, and we know that each of those nitrogens is going to bring 5 electrons, and we'll get 1 extra electron from the negative charge. We know that we have 16 total electrons, so we'll start out drawing those 3 atoms in single bonds in between them. That accounts for 4 of our electrons. We have 12 left. We're going to add 6 to each of the outside nitrogens, and that's going to give us 16 total electrons. That gives us the right number of electrons, but notice that the central nitrogen does not have an octet, so we need to move some of the outside electrons into double bonds. We're going to move outside electrons into double or triple bonds to fill the central octet. Notice in the molecule that I've drawn, I moved 1 set of electrons from the left nitrogen to a double bond and 1 from the right to a double bond. This is the Lewis structure that we'll assign formal charges to. When we assign formal charges, we notice that the nitrogen on the left has 4 electrons that are not bound, and we get 2 electrons from the double bonds, 1 from each bond. And so we take 5 minus 6, and we end up with a -1. The nitrogen in the center has 1 electron from each of the 4 bonds, and so we take 5 minus 4, and we end up with a +1. And the nitrogen on the right is exactly the same as the nitrogen on the left. Formal charges really can be a great way to assess how good a Lewis structure is at representing reality. Generally, the things that represent reality the best are the things that have the lowest overall formal charges. So compare this azide molecule to these other 2 Lewis structures that we could have drawn for the azide molecule. Both of those structures have the same number of total electrons, but they have a much higher formal charge on one of the nitrogens. And so whilst that each of those structures will contribute some of the character of the molecule, they're less accurate at representing what's really happening in the structure. Once you've been doing formal charges for a while, you might realize that atoms usually have a few different formal charges available to them, and that they are always associated with bonding patterns. For example, carbon normally has 4 bonds. As long as it has 4 bonds, it will always have a formal charge of 0. If it has 3 bonds and a lone pair, it will always have a formal charge of -1. And if it has 3 bonds with no lone pair, it will always have a formal charge of +1. Notice that in this example, where carbon is positively charged, there are only 6 electrons. There are very few examples where we don't have a full octet, one of them being a carbocation, a positively charged carbon, another being boron, and the last being hydrogen as H+, where it doesn't have its full duet. And these are exceptions rather than the rules. Now notice with this carbon, that's a carbocation, the positively charged carbon, that carbon is unstable because of the charge. It's also unstable because it doesn't have a full octet. Notice that for all of the other atoms that have full octets, as we move electrons from bonds to lone pairs, the formal charge becomes increasingly negative. So we have 4 bonds here on nitrogen. As we move some of those electrons into a lone pair instead, as a neutrally charged nitrogen, the formal charge is now neutral. And when we have just 2 bonds on nitrogen here, and then 2 lone pairs, we end up with a negative charge. A similar trend is observed with oxygen, positive with 3 bonds, neutral with 2 bonds, and negative with 1 bond. That's generally true. You move more electrons into lone pairs, you end up with a more negative formal charge. In an atom or an ion, we can assess oxidation state as a way of keeping track of electrons. Since many of our electrons involve pluses and minuses, finding their happily ever after, we often try to manipulate the charge on an atom. When you change the number of electrons associated with an atom, this is called a redox, or short for reduction oxidation reaction. To keep track of electrons in these situations, we use the concept of an oxidation state. Oxidation state differs from formal charges only in the way that we deal with electrons in a bond. All electrons in a bond go to the more negative atom. Otherwise, the calculation is the same. So if we look at the oxidation state of this fluorine, we see that we still expect it to have 7 valence electrons, but we count all of them towards the fluorine, and we have an oxidation state of -1. If we look at the case of hydrogen fluorine, we then see that it will have the hydrogen getting nothing from this bond, and so we end up having a formal charge of +1 on the hydrogen. And the fluorine, we would expect 7 electrons, but we get 2 of the electrons from the bond and 6 non-bonding electrons for a total of 8, and we end up with a formal charge of -1. It's very uncommon to have oxidation states of 0 in organic chemistry. These oxidation states have little to do with stability, unlike formal charge, but we are going to see these as being very important, especially for biochemistry, where a lot of these oxidation reactions are how we drive energy through the cells. So let's practice some. Pause this video and try to identify both the formal charge and oxidation state for every atom that's shown. Write it on the paper that you'll bring to class, and then continue the video. So for formal charge, we notice that all of the atoms have the exact same number of bonds that we'd expect them to have. All the hydrogens have 1 bond, and so they get 1 electron from that bond and are neutral. All the carbons have 4 bonds, and so they get 1 electron from those bonds compared to the 4 electrons that carbon comes with and ends up being neutral. And all the oxygens have 2 bonds, and so oxygen also ends up being neutral. This means that these are all good Lewis structures. These are probably the most stable form of these molecules, the best Lewis structure that we could draw for them. Oxidation states are going to differ depending on where we see the atoms. And so if we look at the hydrogens are attached to either carbons or oxygens, and both carbon and oxygen are more electronegative than hydrogen. Remember, hydrogen is between boron and carbon in electronegativity. And so we'll see every hydrogen is the least electronegative atom in a bond, and so it's always going to end up with a +1 charge for oxidation state. Oxygens are generally the most electronegative thing in a bond, except for when they're bound to fluorine, which is rare. And so usually when we see oxygen, unless it's bound to itself or fluorine, as a -2 charge. So in both of these cases, oxygen is -2. Now there are 2 ways to get the carbon structure. We could actually count the electrons, or we could know that the molecules are always going to be neutral. So if we have 4 positive charged hydrogens, we know that we have a -4 charged carbon. Or we can say there are 4 bonds to hydrogens. Carbon gets all of those electrons, all 8 electrons, so 4 minus 8 is -4. Either way, the carbon on the left has a -4 oxidation state. The carbon on the right only gets the electrons from the hydrogens, and so it has 6 electrons. It doesn't get any from the bond to the oxygen, and so we have 4 minus 6 equals -2. And the carbon on the right gets 4 electrons from the hydrogens, but it doesn't get any from the bond to oxygen, and so we end up with 4 minus 4 equals 0. Now we also want to talk about how we could draw things that aren't Lewis structures. If we try to draw Lewis structures in 3-dimensional structures, we can end up with a pretty big mess. We haven't even drawn the lone pairs on this structure, and it's still pretty difficult to follow. This is a molecule of ATP. So typically, we're going to assume that 3D geometry is going to be present, but we don't draw it out. So notice between the last slide and this one, we've had all the dashes and wedged lines disappear. This is called an expanded structural formula. Every bond we show is explicit, but we assume the geometry. But we can make this a little bit simpler, and we usually do by grouping all the H's that are together on an atom. H's usually are present on most nitrogens and on most carbons, and so instead of trying to draw each H out together, we're going to collapse them onto the atom that they're connected to. So notice we have the H's are just shown right after the O's, or the C's, or the nitrogens. That makes it a little bit easier to see. We're still assuming geometry. This type of structure is called a condensed structural formula. This is a pretty common way, especially in biology, to draw out molecules. We can also just assume that the H's are there, but not show them, especially on carbons. We usually show the H's on everything besides carbons, but we don't show the H on carbons. When we draw this type of structure, it's called a skeletal structural formula. Every atom is explicit except for hydrogens, and the geometry is still assumed. This makes it a little bit easier to see what's going on with the molecule. This is used occasionally in biology, but not often. Now, to make structures even simpler, most of the time we actually assume the carbons as well, since carbons make up most of our molecule. So we assume that carbons are present if we have an endpoint of a line that's not labeled. And all the hydrogens that attach to the carbon are also assumed. This is called the line angle structure. And this is by far the most common way that we draw molecules in organic chemistry. Let's have some practice drawing things as a line angle representation. Remember that every time you draw a line angle, we're not going to draw the carbons, but we'll still draw all the bonds between them. So we're essentially drawing the same thing over again, and just not drawing the carbons or the hydrogens that are attached to them. Pause, make a best guess at what you think a molecule will look like, and then advance the video after you've made an attempt at each of these molecules. So these are the answers to the line angle structures. Notice for the top molecule, each unlabeled intersection represents a carbon. None of the hydrogens on the carbon are drawn, but we still just draw a hexagon like we had before. The second molecule down has a group in parentheses. Groups in parentheses are a way of indicating that they're coming off of a main chain. So if we have a CH3 that's bound to a CH, and then bound to a CH3, and then another CH3, we draw that as you see on the right. Other atoms and the hydrogens that are attached to them are always drawn. So on the third molecule down, we see that there is an OH. That OH is maintained in the line angle structure. We don't have the hydrogen on the oxygen disappear, and certainly not the oxygen. The fourth molecule down, we see that there is a CHO group. And if we only attach a C and an H and an O, we end up needing to have one extra bond. And so oftentimes our double bonds are inferred based on the number of hydrogens that are present in an expanded formula. So in this case, we knew that there was one bond to the carbon before, there's one bond to the hydrogen, and there's at least one to the oxygen, and we know that the oxygen needs a second bond. So that's how we know that we have the double bond to oxygen on that fourth molecule. The final molecule, we have 3 carbons in a row, and then the very last bond is to a nitrogen, and the hydrogens are still shown. We can also go the other way. So we can take a line angle structure and we can draw it as a condensed structural formula. Those are the ones with all the hydrogens shown, but grouped onto the carbons. So pause, make a best attempt at drawing each of the following as condensed structural formulas, and then advance the video. For the top molecule, we see that again we just have to redraw that same shape, but now we have to label each of the corners. So every place we had a corner, we're going to put a carbon there. And we can tell how many hydrogens we need based on the fact that we know carbons always have 4 bonds. So in each case, the carbon already has 3 shown, so the hydrogens are only 1 in each of the corners. The next molecule down has 3 carbons in a row with a double bond to oxygen in the middle. We draw that same structure and just label each of the carbons. The carbon on the left and on the right have only 1 bond shown to them, which means the other 3 are hydrogens that are not shown. The third molecule down has a sulfur in between 2 carbons, and so we draw that out, and each of those carbons again only has 1 bond, and so they each end up having 3 hydrogens that weren't shown in the line angle that we show in the condensed structural formula. And finally on the bottom we have an oxygen that's between 2 carbons. The carbon on the left has just the bond to the oxygen, so it needs 3 more hydrogens to fill its octet. And the carbon next to the oxygen on the right has a bond to the oxygen and a bond to another carbon, so it only needs 2 hydrogens to fill its octet, so it's a CH2. And then the final carbon on the right is a CH3 again.